This video will demonstrate the steps for the gravimetric analysis of phosphorus in a common all-purpose plant food. Our goal is to use this analysis to assess the accuracy of a reported value of phosphorus in this plant food. This diagram provides an overview of the experimental approach. A defined mass of plant food containing P2O5, diphosphorus pentoxide, is dissolved in water, which essentially results in the aqueous hydrogen phosphate anion. This anion reacts with an excess of aqueous magnesium plus 2 from 10% magnesium sulfate and a slight excess of aqueous ammonia to produce the magnesium ammonium phosphate hexahydrate precipitate. This precipitate is collected by vacuum filtration, dried and weighed. From the mass of magnesium ammonium phosphate hexahydrate and the stoichiometric mole ratios in the balanced equations and chemical formulas, the mass of diphosphorus pentoxide in the original food sample can be determined. We start our experiment by precisely weighing 0.5 grams of the plant food with an analytical balance. The brand of plant food used in this experiment is called plant prod and has a fertilizer composition of 10, 52, 10. Of course, it is the number 52 which is of interest to us, as it represents the percent mass of diphosphorus pentoxide in the plant food. We now find Scott in the lab making this mass measurement. Notice his careful attention to recording all relevant data, including the brand name and details about the plant food. Scott zeroes the balance and then tears the weigh boat. As is typical in acquiring a target mass, Scott requires two separate mass measurements to finally arrive at the desired mass of plant food close to 0.5 grams. Please note that after watching this video, you will have access to a link in Moodle, which will provide you with your assigned mass values for this and all other relevant measurements. Also note that this entire procedure is performed in duplicate. The plant food is then dissolved in about 20 ml of deionized water. While some brands of plant food may contain some insoluble material and therefore require a filtration step, it has been our experience that the plant prod brand is highly soluble and produces a homogeneous solution. As shown in this diagram, when diphosphorus pentoxide, our compound of interest, dissolves in water, it produces several aqueous products, from phosphoric acid to phosphate. These products are in equilibrium, and their relative concentrations depend on the pH. During the precipitation step, the solution will be made slightly basic, and the hydrogen phosphate ion, the anion required in the precipitation, will dominate. We now return to the lab, where we see Scott quantitatively transferring the solid plant food powder to a beaker. Notice that he is careful to ensure that the glassware is clean and that all the powder is transferred from the weigh boat to the beaker. To ensure a complete precipitation of the hydrogen phosphate ion, an excess of magnesium cation is added. The volume of 10% magnesium sulfate required can be determined by a quick calculation, as described in step 3 of the procedure. Assume, for instance, that exactly 0.5000 grams of plant food is measured. Multiply this by 0.52 gives the mass of diphosphorus pentoxide, which is then multiplied by 5 ml per 0.1 gram to give the volume of 10% magnesium sulfate required. Back in the lab, we see Scott doing a similar calculation for his specific mass of plant food. With the calculation done, Scott measures the appropriate volume and adds it to the aqueous plant food mixture. In the next step, a slight excess of 1.5 molar ammonium hydroxide is added. The ammonium ion is obviously involved in the chemical formula for the precipitate, and the hydroxide ion will produce the appropriate pH so that the hydrogen phosphate ion predominates. To ensure that we add only a slight excess of 1.5 molar ammonium hydroxide, a few drops of the phenolphthalein indicator are added to the solution. The ammonium hydroxide is added only to the point when the indicator turns a faint pink color, which will look purple given the blue background, which indicates that the solution is slightly basic. In the lab, we see that Scott has moved to the fume hood. This is because the ammonium hydroxide is very volatile and highly caustic. Notice that he turns on the light, the fan, and then adjusts the sash to the appropriate level. It takes several additions of the ammonium hydroxide, with frequent mixing with the stir rod to achieve the appropriate pink-purple color. You may be wondering why it is important to add only a slight excess of ammonium hydroxide. Recall that this chemical is not only the source of ammonium ions, but also hydroxide ions. Recall also that we have an excess of magnesium ions. If we add too much ammonium hydroxide, we risk that a secondary precipitation reaction will occur in addition to the desired precipitation reaction. It is useful to reflect on how this experimental error would impact our estimation of phosphorus in the plant food. We will wait at least 15 minutes for the precipitation reaction to be complete. But in the meantime, we can weigh a sintered glass crucible, which will be used in the next filtration step. A glass crucible has a very small pore size, so that most of the precipitate will be collected. Further, unlike a filter paper, the sintered glass is resistant to damage from corrosive materials like ammonium hydroxide. Here we see Scott weighing the empty crucible. This mass can be subtracted from the mass of crucible and precipitate to find the mass of the precipitate alone. In the next step, a vacuum filtration is set up, and the precipitate is quantitatively transferred to the crucible. Several low-volume washes with deionized water can assist with the transfer. Although the filter flask is secured with a clamp to the retort stand, Scott sits the filter flask on the base of the retort stand as an added precaution. A squirt of deionized water helps ease the vacuum tubing onto the arm of the filter flask. It is a good idea to test that an adequate vacuum is achieved with the water aspirator. Here, Scott demonstrates two kinds of crucible or funnel holders that allow for a vacuum seal on the filter flask. Notice that Scott breaks the vacuum by pulling up on the crucible holder, and only then does he turn off the aspirator. The filtrate is disposed of in a waste beaker, and then the vacuum filtration is reassembled for the isopropanol washes. The isopropanol washes are collected in a separate waste beaker. The crucible is placed in a beaker, which is labeled with Scott's name, the chemical formula, and the trial number. The precipitate is dried in an oven at a temperature of about 50 degrees Celsius for 48 hours. The dried crucible and precipitate are weighed. Again, a reminder that after watching this video, you will have access to a link in Moodle which will provide you with your assigned mass values for all the mass measurements in duplicate.